Hi, my name is Ian Nessler, and I'm a chemical engineering student in the PhD program at the University of Michigan studying cancer therapy. Today I'm going to talk about my efforts to optimize a certain type of cancer therapy, but first we need to understand what cancer is. You see, cancer occurs when a healthy cell has some sort of damage that causes it to rapidly grow, uncontrollably. As those cells continue to grow, they'll often impact organs or other vital components of our body that are required for us to survive. So we try to remove them. It's been almost 200 years that we've been developing cancer therapy, and first we started with surgical removal, basically going in and physically taking out a tumor. It worked for a while, but there are certain tumors that you're not able to remove the whole mass, and so you'll leave a couple cells behind that can continue to grow and cause the patient problems later on. So we opted for chemical types of therapies. Many of you are likely familiar with chemotherapy or radiation, and when I mentioned those types of therapies, it's likely that you thought of side effects, such as nausea, vomiting, and hair loss. You see, although these therapies are an improvement, they still have a lot of side effects because they target rapidly growing cells. I mentioned earlier cancer cells rapidly divide, and that's why these agents work against cancer. But we also have a lot of healthy cells that rapidly divide, such as your hair, the lining of your stomach. And so when we give these agents, they also act in those locations, causing damage that causes these side effects we see. The final area of therapy that I'm going to talk about, which my research is focused in, is targeted therapy. You see, these agents are also targeted towards cancer therapy, but it's not based on how rapidly they grow. Instead, it's based on what they present on the cell surface. And so, we can be much more specific in targeting cancer cells and leaving healthy cells untouched. My area of interest in targeted therapy is specifically antibody-drug conjugates, or ADCs. They act in three main ways, which I'm going to liken to a pizza. You have a base method, which would be the crust or the foundation that we're going to build upon. There's a secondary action, which is going to be the sauce, and then we can also add things to the antibody to make our toppings. Just like on a pizza, there are many different toppings. There are actually a ton of ways in which we can modify antibodies to develop the most effective drug compound. I'm going to walk through the individual components of an ADC, as well as the ways in which they act on cancer to deliver the most efficacious treatment. The main component of an antibody-drug conjugate is the antibody itself. As a part of a healthy immune system, everyone develops antibodies. These protect you from germs and pathogens. Some common examples of where you would develop antibodies are like for vaccines. If you go in for a flu vaccine, you're actually being given a dead virus that your body can then interact with and recognize and develop specific antibodies against. The reason that these antibodies can provide long-lasting protection is due to their specificity. And if we can repurpose an antibody to recognize a cancer cell, and only a cancer cell, we can improve patient outcomes. You can think of them like the pizza delivery guy. When you call in, he has a ton of different houses that he could go to, but he knows which house to go to because you've told him where to go. And in that way, scientists have actually developed antibodies that know where to go. They know to go to cancer cells only and not to healthy cells. So the antibody will recognize the cancer cell, just like the pizza man will deliver it to the correct house. As I mentioned before, there are three main mechanisms in which ADCs can act. Two of those stem directly from the antibody itself. An antibody binding to a cancer cell actually blocks signaling inside the cell that causes it to die. This is the most basic way, because it's just the antibody interacting with the cancer cell. I liken this to a pizza crust. Just like a pizza crust is the most basic ingredient for a pizza. The second method in which antibodies can cause cell death is by interacting with the immune system. I mentioned earlier that as part of a healthy immune system, everyone has antibodies, and your body can interact with those antibodies. So, when your antibody coats a cancer cell, the immune system will actually come in and kill the cancer cell as well. The final part of an antibody-drug conjugate is the drug. As I mentioned earlier, the antibodies are specific, and just like a pizza delivery guy, they can serve as a transporter for a drug that we've attached to them. We can even attach chemotherapy drugs that are too toxic to deliver on their own and provide specific cancer cell death. In this way, we can avoid side effects. To put this on a larger scale, if an antibody was the size of a human, the drug would be about the size of a baseball. So if I asked you to pick up 2 to 3 baseballs and take them from one location to another, you could probably do that. Just like the antibody-drug conjugate, ADC can carry a couple drug molecules from the site of injection to the tumor cells. This is our third and final way in which an ADC can kill a cancer cell. Once the antibodies interacted with the cell, the drug is free to go inside the cell and cause cell death. I liken this to the toppings of a pizza because there are so many drugs out there. We can use any of the chemotherapy agents that are used in the clinic. We can even develop other drugs that are even more potent and attach them to an antibody and use those. So now we have these three building blocks that we can use to develop the perfect drug or the perfect pizza. But just like people, cancer is unique. It doesn't always like the same thing. Just like if I polled a room and asked what their favorite pizza type would be, not everyone would say cheese or pepperoni. There'd be a lot of different options. So I'm studying what kinds of options are best for certain types of cancers. We can mix the binding, the immune cell function, as well as different drugs to see what's the most effective. And in that way, I'm hoping to create a cancer therapy, but also to make a perfect pizza. Although we've been working on cancer therapies for over 200 years, we have yet to find a single method to treat all cancers. The truth is we may never find one single method, but by understanding the ways in which our current drugs act, we can improve upon them and try to better patient outcomes.